Thanks for coming to this talk on scaling the Neo4J write path using Spark and the BatchImport API. So my name's Dexter, and I work for a company called G Research, and we are the leading quantitative finance research firm in Europe. And today I'm going to be talking to you about a couple of different things, but before we get going, here's my social details and also some for the company. So if you'd like to ask any questions about what you hear here today, or just about the company in general, then do feel free to reach out. Today I'm going to be going through an interesting problem that we had while trying to load a large amount of data into Neo4J, but being unable to use the Fabric API, as well as how we actually worked around this and got it to perform faster than ever before. So first off, I'll start by discussing all of the general scalability things that you can expect in Neo4J, then how you can use the offline loader and make it much faster than the default version, then how you can use the Lambda architecture to take this into production, before quickly discussing further things that could be done to improve this. So first of all, that scalability. Historically, Neo4j could only scale vertically. That meant that you had to just get a bigger box if you ran out of space. Quite a while ago, they added in Enterprise Edition the ability to have causal clustering and things like that, which allowed you to scale the read path very easily. So you can scale the read path horizontally, which is nice. Unfortunately, that is only the read path. There's still only a single writer, so that is inherently quite a big limit. But a couple of years ago, they released something called Neo4j Fabric, and Fabric allowed them to recently demonstrate this, the trillion graph, which is a graph containing over 1 trillion relationships. It took them over 3 hours to load it and covered 280 terabytes of data. That's pretty good. We only had 500 gigabytes to load, and we had 24 hours to do it, so seems like it should be easy enough. Unfortunately, while Fabric's great, it does have a few limitations. The most important one for us was that the sharding structure leaks into the queries, so you have to actually be aware of the sharding structure ahead of time. It also doesn't have great big data integrations, at least not yet, and the cost can be quite high. But it is a fantastic tool if it works for you. It lets you join multiple sets of databases together, which is fantastic, and it comes with all the sorts of enterprise features that you might expect, like Kerberos. So it really is a great tool. Unfortunately, we couldn't use it. So if you can't use Fabric, how can you load a huge amount of data into Neo? Well, there's 3 main ways to load decently sized amounts of data into Neo. First off, you can just batch it. Neo being an ACID database, the biggest limitation in terms of scaling is simply that you have to acquire a lock in order to do a write. That means if you have larger batch sizes, it writes faster. Well, maybe not faster, but the cost is amortized over the batch, so it ends up being much more efficient. Unfortunately, you still end up doing a lot of work on the nodes themselves, and there's still only one writer. So they recently added the Spark connector. This allows you to actually use Spark instead to do a lot of the pre-work, and then you can take that output from Spark and dump it straight into your running Neo instance. Unfortunately, it's still limited in exactly the same way. You can still only have a single writer node, so while it does a lot of the hard work of parallelizing for you, so that you can parallelize to the maximum extent that you can, but unfortunately, it still has to acquire those locks, which ends up taking a lot of time. And if you are fully maximizing it, then that will be impacting the performance of the rest of your system. So if you have live data flowing in as well as this large data set, then you'll come into issues. So if you don't want to do either of those things, the third option they provide is the admin import tool. This is intended as an offline thing to sort of initially bootstrap your system, though you can also use it in live systems, as we'll see later. The slight problem with this one is that it requires you to use a specific format of CSV or a couple of other formats, but it can only load into offline instances. In fact, that's even taking it a little bit far. What it really does is create an entirely new Neo4j store. That Neo4j store can then just be made available to a Neo4j instance, which will index it and start it up. So initially, we started off by using the Neo-semantics library that they provide. This does a lot of the automation for you, and is really, really easy if you want to just work with RDF data, which is what we had. We had about 500 gigabytes of it compressed. Unfortunately, after 7 days, I killed the process because it was still running. That's not really great, but when we benchmarked it, we found that most of the time was essentially just spent parsing and doing all the pre-work. Very little work was actually being done on the Neo node itself. So, okay, what happens if we try that Spark approach? So we did a bunch of pre-work in Spark, trying to cut things down as much as possible, make the strings shorter, convert some types over, etc. But it still didn't work. It only took us down to about 2 days. After 2 days, I killed the process. So still not quite there. We're still limited by that single writer. So clearly, we're going to have to use the offline loader. But how does that perform? Well, building on top of that Spark app that we had previously, we already had a lot of that pre-processing work done, so we just changed it to output the CSV files that are requested by this bulk loader instead. That cut the size down a bit because we were now using much more efficient storage, so we didn't have a lot of the duplication. We'd shortened some strings, things like that. So we'd taken it down from 500 gig to 300 gig. This went better. It loaded in 27 hours, which is still just over the 24-hour limit that we wanted. But at this point, 32 cores, 256 gig of RAM, I could have just got a bigger machine, and it would have hit the limit that we needed. But it really wouldn't have given us much room to grow. And this was just our first test data set. We needed to add in more data sets like this. We needed to do it without impacting production. And we needed to also allow live data to flow in at the same time. So at this point, we were talking to the Neo4J performance experts, and they pointed out that the admin loader actually uses this interesting thing called the BatchImport API under the bonnet. The BatchImport API is interesting. It used to actually be under the unsafe package, but it's not unsafe in the sense that it is a changeable API, but rather that all the checks and balances are gone. It is very easy to create a corrupt data file using this system if you don't know what you're doing. But as long as you know your data set, it's fairly easy to come out with something that works. And that means, again, when we benchmarked this, we found out that almost all the time was simply just spent parsing these CSVs. If we weren't using that CSV, if we were using something that was much more friendly to Neo, maybe it'd be faster. So we gave this a try. And thus was born the G-Research Lightning Loader. The intended process goes like this. Data comes in, we put it onto HDFS, and if it's small enough, we also stream it into the current live instance. We then, on Spark, take all the data that we've got, do that same pre-processing as before, but this time we take it a little bit further, and we make something that's much more friendly towards Neo. So rather than just CSV files that are lots and lots of strings, we're instead going to do this a slightly different way and try and output actual Java types, because the Neo4j loader with the Batch API is Java. So if we can move things in portable Java types, it's going to be faster. It's also going to be a lot more efficient, because most of the data that we were working with was numeric. So by not using strings to represent numeric data, we end up saving a lot of space. In terms of actually writing it out, we then write it out using a custom Hadoop output format, the code for which is available and linked later. The output format is using sequence files and also using the LZ4 compression. The reason for picking LZ4 for this is basically because LZ4 is very, very quick to read on the client side. And remember, you can still only do this loading from a single node. Once you've got those output files, you use that BatchImport API to tell Neo about them. It loads them up. Then you start it up, wait for it to index, and that's it. All you have to do is switch the load balancer, and you are done. So how did it work? Well, pretty well. 27 hours down to 40 minutes. I count that as a win. It actually turns out that the 500 gigabytes that we initially started with, once you get rid of all those strings and turn it into native data formats and compress it with LZ4, you end up at only 50 gigabytes, which is going to be much faster to send around. And actually, at this point, more than half of our time is spent doing internal batch loading operations. And you probably can't see this from too far back, but we did a little bit of benchmarking here. And you'll see that there is still some stuff that looks a bit custom here. This wouldn't be here in production. The only reason that's there is for testing purposes. So that bit would go away. This means we would, in fact, end up with a reasonable amount more than 50%. But there's still more that could be done to improve it. But at this point, considering our aim was 24 hours, I think we've hit our goal. So how can you take this into production? Well, the Lambda architecture is a system by which you have three main components. You have a batch section, where you use something like Spark or Hadoop to process all your data and produce views into some kind of read-only store. Then, on top of that, you add in any additional new data using a speed layer. When you consume from the speed layer and the batch layer at the same time, then you end up with the complete system. So, with a slight variant on this, here's our system. Raw data flows in, goes both to Kafka and Hadoop. If it's small enough, it's going through the Kafka system straight into the hot instance, but always going to Hadoop regardless. Spark starts up, takes note of where the Kafka offset is, takes all of that data, and then pre-processes it in that way that we discussed. And that's gone away. How exciting. There we go. Now that the data has all been pre-processed, it gets put into a place that it can be accessed by that loader. Then the Lightning loader runs, creates a new store, Neo starts up. We take note of that offset that we had before, stream in any new data that's arrived since then, and switch the proxy. If you're using causal clustering or something like that, you'll need to change over about half of your read followers before you switch over the main proxy. But it is essentially the same system. So this is going to break every time I change slides. Please, no. Oh, we're back at the start. Sorry about that. Yes, so improvements that we could make. There's still some improvements that can be made to this system. In particular, at the moment, we write the whole thing before we start reading it. If we skip that step and simply wrote it to Kafka, which is already in the system, then we'd be able to start that loading process sooner. We also lose a reasonable amount of time, in particular actually processing enums, because it turns out that custom Hadoop output format, while it helped us a lot, enums are really inefficient in that. They actually get written as strings. And strings are actually written as the length followed by all the data. So actually, if we just sent over the ordinal, it would be a lot faster. And actually, a fair amount of the data, because it's quite enum heavy, ends up being these strings. So that would be a potential area for significant improvement. That said, this stage only takes 5 minutes at the moment, so it's not really worth improving at this point. We could also just output the Neo4J types directly, and you could speed up Neo4j itself by doing things like putting the string store on its own separate disk, or indeed, potentially even use Spark to create the entire store. This is quite hard, because you'd have to replicate what the BatchImport API is doing. And the hardest part of that is that it has to know all of the IDs that it's working with. So you would need some support from Neo4j themselves to make sure that this didn't become incompatible. So we'll leave that for the future. You could also use something like Graal to use this API from a language other than a JVM language, because by default it is only available in Java, but Graal allows you to use it from things like JavaScript, for example. So I have some links here for further reading, including a link to a blog where I go through this in more detail and provide all the code for the batch import system, as well as that Hadoop output format, the custom one, which helps out with all of this. So if you go to that blog, you can get all of that code and try it out yourself. I did try and keep it simple, so there are some bits missing out, but all of the hard code is there for you to use. So these are some of our principles at GR. I feel like this process was embodied by these three in particular. We had a hard problem. I was empowered to go and talk to the Neo4j performance experts who helped us solve it. We just kept trying lots of different things. We didn't get stuck on something. And then we just were pragmatic at the end. As I said, there's plenty of areas for improvement, but with a 40-minute runtime and only 5 minutes being spent on that initial stage, we can leave those things for later. So if you'd like to be supported in solving hard problems and pushing the limits while having a good laugh, why not come and join us? We're always looking for more talent to push us beyond our limits. And I think I have 2 minutes for questions.
I have one, which is like technical details.
Yep.
What was the format that you used to store it into HDFS?
So the question is, what format did we use to store the data in HDFS? The answer is what it came in as in the first place. So when it came in, it was just a lot of RDF data as just compressed gzip files. So as the data flows in, it gets written directly to there, and then Spark can read that inherently and process it from that point. Obviously, reading gzip is relatively slow, but we can't really help that because it's how the data comes in from the external provider.
All right. And it wouldn't help to put like some kind of stack that will convert it into a more usable format before putting it into HDFS?
So the question is, would it be faster to do something to convert it into a more usable format before putting it in HDFS? I don't think so. Simply because at 500 gigabytes, it takes quite a long time to unzip that file. So if you were going to do that essentially twice, you unzip the file, then you have a lot of files that you put on HDFS and read them, I think you'd lose so much time to that that it really wouldn't help. Yeah. Time's up.
Well, actually, it's just like concerning the whole architecture. For example, you say you have Kafka and stuff, but do you install it yourself, or how do you maintain that?
Yeah.
Do you have a wall solution, an on-premise solution that proposes you to stuff?
Yeah, all of this is on-premise.
Okay. What is it? Is it like an external provider that proposes you this solution, or did you install it in your company?
I didn't personally, but it is installed by the company. We have our own department that manages all these things.
Okay. All right.
So we are out of time. If you have any more questions, feel free to ask me just offline or message me from any of the social things at the front there.